Hello, statistics students. In our last section, we were introduced to hypothesis testing. When in our last chapter, when we did confidence intervals, we were making an estimate of a population parameter, either the mean, mu, or the by proportion, p. In this chapter, we're going to make hypotheses about them. So rather than just saying mu is between these two numbers, we're going to say mu is greater than 50, something like that. And then we're going to test and see if we can get evidence for mu is greater than 50. So in this lesson, we're actually going to start doing a hypothesis test, and we're going to do the simplest one. Just like we started with the simplest in confidence intervals, we're going to do a hypothesis test for mu, assuming that we know the population sigma. Now, you heard this a couple of times in our last lesson. I'm going to say it again. This is a biggie. This is probably what you're going to remember. If you remember anything from this class 5-10 years from now, you're going to remember this. If p is low, reject the hoe. In other words, if our p value is lower than alpha, we're going to reject the null hypothesis. And remember that a p value is an area under the curve, and it's defined by three conditions. One is the probability of getting the results, the sample results we got. So our sample is either x bar or p, because those are the only parameters we're testing. Or something more extreme. If you recall, because the normal curve and the t curve are continuous, the probability of getting any one value exactly is 0. So we're going to have to go more extreme and shade an area under the curve. Assuming the null hypothesis is true. Now, we assume the null hypothesis is true because the null hypothesis has the equal sign in it. So if I want to assume, if I want to test the probability that mu is greater than, that mu is less than something, my null hypothesis is that it's greater than or equal to mu 0. That means the smallest possible value that I'm going to assume is true is mu 0. Because if mu is way over here, mu 0, and that's called the null value. That's just the number we're testing. That's the 50. If I say mu is less than 50. So if the mu 0 were way over here, then the curve would be way over here. And getting an x bar way over here, that probably would be pretty strong evidence that mu is less than mu 0. But to make it absolutely the safest we can be, the most conservative estimate of all, mu would be equal to mu 0, and we still want to see if it's less than. So we put the equal sign in the null hypothesis. That tells us in the most extreme case, mu is right here. It's not any further to the left of here. Now, here are the sample results we got. Here's something more extreme, assuming that the curve really is centered here. This area under the curve is my p-value. It's my probability of getting this sample result or something more extreme if the curve is centered here. And the smaller that area is, then the more unlikely that is to happen, because it's probability, it'd be a smaller probability. And so we say, if that happens, it's unlikely that this is true. So let's say that this ended up being a pretty large value, certainly greater than 5%. It's possible that mu is less than this number. It's possible that mu is over here. And that's why we got an x bar the way we did. So let's review the central limit theorem. The central limit theorem says given any population with a mean of mu and a standard d of sigma, this certainly is not a normally distributed population. If n is big enough, and remember we saw some populations where n could be as small as 3 or 5 to be big enough, but in any case, once you get to 30, it's pretty much always big enough. If n is big enough, your sampling distribution will be approximately normal, with a mean of mu, same mu, and a standard dev of this standard dev divided by the square root of your sample size. And you'll recall why that is, because averages don't move as much as the actual data points. So let's talk about p-values. We have, if we take a data set and find its average, if we were able to plot all possible samples of size n and take their averages, we'd have an approximately normal distribution with a mean of mu and a standard dev of sigma over root n. We want to convert that to standard normal so that we can use our normal curve table. So you might recall that our z-score was a sample value minus a hypothesized value divided by a standard error. Turns out a t-score is the same thing, just the standard error is going to be written differently. So we're hypothesizing about mu, so our sample value is x bar. Our hypothesized value is mu0, whatever we're saying mu is greater than or less than. And our standard error of this curve, because this is the curve we're looking at, would be sigma over root n. So this is our z-score. And that will allow us to find an area under the normal curve. On page 365, you get that same formula and some guidelines for doing a hypothesis test. If you have forgotten how to use the normal curve to find, or how to find an area under the normal curve, please refer to page 266 in our current textbook. If you're watching this video many years after I make it, it'll be a different page, but you can look up how to find an area under the normal curve. So on page 366 of the book, we have a problem. It says, homeowners claim that the mean speed of automobiles traveling on their street is greater than the speed limit of 35 miles an hour. A random sample of 100 automobiles has a mean speed of 36 miles per hour. Assume the population standard dev is 4 miles an hour, so they're giving us sigma. Is there enough evidence to support the claim, and the claim is that the speed's greater than 36, at alpha equals 5%, use a p-value. So let's write down everything we know. So we're trying to prove that mu is greater than 35 miles an hour. Since that's what we're trying to prove, we're going to make it the alternate. Now, FRL has a very different way of determining what's the null and what's the alternate. I insist that you do it the way I'm teaching it. So in this case, they're going to be the same thing. The null is greater than, the mean is greater than 35, which means our null is going to be less than or equal to 35. Now, you could write this either as the complement, so the complement of greater than 35 is less than or equal, or you could just say mu equals 35, because we're trying to gain evidence against this statement anyway. We said alpha is 5%. In other words, if the probability ends up being less than 5%, we're going to say that's so unlikely to happen by chance that this must be wrong. Okay, our X bar, after we wrote the hypotheses, then we gathered data, and we came up with an average speed down the street of 36 and a standard dev of 4. Is that enough enough evidence to say, yeah, people are speeding down the street? Now, granted, they may not be speeding much, but they are breaking the speed limit. So we calculate our z-score, our sample value minus our hypothesized value divided by a standard error. There's our sample value. Here's our mu0. Mu0 is just this number that's in our hypotheses. And if we're taking averages of groups of 100, the standard dev isn't 4, it's 4 over square root of 100. And we get a z-score of 2.5. We graph our normal curve. So here's one standard dev, which would be 4/10. Two standard devs would be 8/10. 10/10 would be 1 complete mile an hour, which would be 2.5 z-scores. There's the area we're looking at. The probability, and again, we're going to state the problem in terms of x, restate it in terms of z, then use the table. And it's not x greater than 36, it's actually x bar, the average speed greater than 36, is the same as z being greater than 2.5. Because it's the area to the right, we do 1 minus the table value. This gives us 62 hundredths of 1%. That's less than 1%, which is certainly less than an alpha of 5%. So what we're saying is if the average speed down the street really is 35, the probability of getting a sample of 100 cars, there's our 100, probability of getting a sample of 100 cars and that sample averaging 36 is very, very low, which means the speed, the average speed probably is over here somewhere, which means the curve is peaking here, and then that you would have a much higher probability of getting this if the average were higher. So in this case, P is low, we reject the hoe. Now we have to write a conclusion statement, and I want your conclusion statements to be in 3 parts. The first part of your conclusion statement is, do you reject the null or fail to reject the null? You never accept the null. You gather evidence, you either have enough evidence against it or you don't. At what alpha level? Because an alpha of 5% on this problem, we rejected the null. In an alpha of 1%, we would have rejected the null, which means there's only a 1% chance that you would get these results, or something more extreme, assuming this is true. But if we had to be really super sure, like life or death, so we wanted to be, only a 0.5% possibility of getting it wrong. In this case, we would fail to reject the null. We would not have enough evidence against this statement at the 0.5% level. 10 times greater at the 5% level, we do have enough evidence. We're willing to be wrong 5% of the time. And then you state your conclusion in English. So for that last problem, my conclusion statement would be, I'm going to reject the null at the 5% level, conclude that the average speed of the cars on the street is greater than 35. In other words, I rejected the null and concluded the alternative is true, but I restated the alternative in English. The problem was given to me in English. I'm going to answer the problem in English. So this would be my conclusion statement for that problem. All right, here's a sample problem for you. Mu0 is 50. I want to know, is the average of some data set less than or equal to 50, or is it greater than 50? My population standard dev is 10. I take a sample size of 25, and I get an average of 51. I'd like you to try this problem. So what you would do, shut the video off and see if you can handle it. Start with, we've checked, we know sigma, we're trying to find the mean, we've got our hypotheses here. Calculate a z-score, shade the appropriate area under the curve, find the area under the curve, that's your p-value, and then what conclusion can you draw? Is there enough evidence to reject this, or is there not? Yes, I have the answer. Please remind me in class and we will go over the answer. There is such a thing as a two-tailed test. You could be either mu is equal to 50 or it's not. I just think they're wrong. It's not 50. So that would be mu is not equal to 50. And you have a two-tailed test. And there's an example of that on page 367 of our current textbook. Current as of when I make this video. Okay, so let's do another example problem together now that you've stopped the video and worked on that one a bit. I think that mu is less than 12, whatever the average is. You know, whatever this is representing, it's less than 12. So here's my null hypothesis. I'm gonna believe the null. I'm not gonna prove it's true, but I'm gonna believe the null is true until I get enough evidence to reject it and conclude this is true. So here are some facts. The population sigma is 2. We're going to always default to an alpha of 5% unless told otherwise in a problem. If you ever use an alpha that's not 5%, you need to explain why. I'm going to take a sample size of 16. Now, again, I've already written my hypotheses. Now I gather my data, and I got an X bar of 11.5. And I'm going to say that my population is approximately normal, and this was a random sample. So let's calculate a z-score. Now, mu is less than 12, so I want z being less than -1. So 11.5 is 1 standard dev away. So again, my null is mu is less than, it's pointing to the left, I'm shading to the left. This area is my p-value. So again, state the problem in terms of x, restate it in terms of z. I want the area to the left, so I just use the table value. Here's my p-value. There's a 15.87% chance that if mu is equal to 12, that I would get a sample of size 16 and you have a sample average of 11.5 or less. That's what this means. So in this case, p is not low. I am not going to reject the null hypothesis. Let's write a 3-part conclusion statement on this. I fail to reject the null in this case. At the 5% level, there's not enough evidence to conclude that the alternate, and we would state that in English, but I didn't give you a scenario explaining what that was. There's not enough evidence to conclude that that's true. Now, when you fail to reject the null, some people say, great, you didn't fail to reject the null. You didn't have enough evidence to say the alternate is true. What are you saying? So sometimes if you fail to reject the null, and only if you fail to reject the null, you can conclude that mu is greater than or equal to 12. So we can conclude that the null hypothesis is true pending further evidence. Write that down. All that means is this time we didn't get enough evidence to reject the null. We didn't prove the null is true, we just didn't have enough evidence to reject it. So what this is saying is until we get more evidence, enough evidence to reject it, we're going to conclude that the null is true. It's kind of like if you were in court where you say, you know, the null hypothesis is that you're innocent until proven guilty. Well, if they fail to prove you guilty, and if we could have double jeopardy, we'd say, well, we didn't prove you were innocent. We just couldn't prove that to reject that and prove you were guilty. So until we get further evidence, we're going to conclude that you're innocent, or at least not guilty. So that's how you can do a hypothesis test using a p-value. There is a way to do a hypothesis test without ever calculating the p-value. Now, some people really prefer this method. Some people prefer the p-value method. I've read many reports where they'll just tell you the p-value. So I'm going to insist that you know both. And some problems on a test, I'll say, what is the p-value? Other problems, I'll just have you do it on your own and you can do it this other way. I want you to know both. So we're going to go to that same problem that we just did. So we know the answer is we're going to fail to reject the null. So here's the same data. So this is at the 5% level. This is a one-tailed test. I'm only interested if mu is less than 12. So I'm only interested in this tail. And this tail, that we know this area has to be 5% or less. So what z-score marks off the bottom 5% of the data? And that turns out to be negative 1.645. How do you know that? Well, think of it this way. If I had two tails, if this were 5, because I'm interested in this 5%. If this were 5% and I had another 5% over here, that would be 10% in the two tails. The area in the middle would be 90%. Oh, that's that number from the 90% confidence interval. So you can use those numbers, or you can just look on the table and find the bottom 5% and you'd get a z-score of negative 1.645. But if you truly understand the normal curve and how to use it, you could say this tail is 5, a mirror image tail over here would be 5, the middle would be 90, and then you could use that z-score, which would be positive 1.645, would mark off the top 5%. You know that the bottom 5% would have to be negative. Anyway, this is what we call my rejection region, RR. If my z-score that I calculate is in here, then obviously the area to the left of it would be less than 5%, because this z-score marks off 5%. Any z-score in this area would mark off an area to the left of less than 5%. And we already said my z-score is negative 1, which is right here. I am not in the rejection region. If I were in the rejection region, I'd reject the null. I am not in the rejection region, so I do not reject the null. And then we are right back to failing to reject, and we do our three-part conclusion statement. So you can either find the area under the curve to the left of this z-score, or you can say, what's the rejection region? Calculate the z-score. And if your z-score is in the rejection region, you reject. Now we're going to do a two-tailed test, the TTT. Everyone likes the TTT. Just cover up some of this for a moment. So here's the data that we start with. Mu is either equal to 20 or it's not. I'm trying to find evidence that mu is not equal to 20. And I want it at the 5% level. My sigma is population standard deviation is 4. I take a sample size of 16, and I got an average of 19.6. Is that far enough away from 20 that I can conclude that this is true or not? Notice again, and I keep saying this, you do your hypotheses first, then you gather data. Sometimes when you're doing problems in a book, because the data is right there, you assume you have the data first, and then people try to do calculations and then write the hypotheses later. That's not statistics. So again, we have normally distributed data. This is a random sample, so we're checking off all the boxes. So in this case, where's my rejection region? My rejection region is, see, at the 5% level, it's a two-tailed test. So the two tails together have to equal 5%. So this area is 2.5%, this area is 2.5%. Well, if the two areas together, because it's a two-tailed test, add up to 5%, then we know the middle would be 95%, and we can look on the bottom left of the normal curve table, and There are our Z critical values. We calculate our Z statistic, we get negative 0.4. Now here's the catch. When you're doing a two-tailed test with a p-value, so here we got a negative 0.4, but we could just as easily have gotten a positive 0.4 on the data because we didn't know if we were going to be above or below 20. So our p-value is the area to the left of negative 0.4 and to a mirror image to the right of positive 0.4. So you can see we have a huge p-value here. So what we're doing is, because we have a two-tailed test and our z-score, our sample data was 0.4 of a standard deviation away from the mean. It was 0.4 below, but still 0.4 away from. Our p-value is going to be anything more than 0.4 of a standard deviation away from the mean in both directions. So we go here and to the left, here and to the right. Clearly, you can see that this p-value, you could find this table value here and then double it because it's symmetrical. That would be your p-value, obviously going to be above 5%. And then if you're using the rejection region method, you can see that we are not in this X bar that we got is not in our rejection region. So both of these are telling us that we are going to fail to reject the null. To find the p-value, I found the area under the left tail and I doubled it because again, it's symmetrical. So our p-value was almost 70%, 68.92%. Greater than 5%, we're going to fail to reject the null. A lot of students start getting confused at this point. So write this down, put a star around it, a cloud around it, star next to it, highlight it, whatever you're going to do. When you're determining whether you fail to reject or reject the null hypothesis, you compare your p-value to alpha, or you compare your z-score to z-critical to see if you're in the rejection region. So this is the p-value method. This is the rejection region method. I want you to understand both of them. And lastly, using our current FRL textbook, check out those guidelines on pages 368 to 370. That was a lot of instruction. We'll go over it in class, especially that one problem where I just had you do it. I know this seems very confusing and daunting right now. Don't worry about it. Within a week or so, this will be old hat. You'll get it. Just like you did algebra, just like you did borrowing, just like you did positive and negative numbers. It seemed scary at first. And then after you did it a while, it's like, oh, okay, yeah, I got this, I'm good. That's what the case is gonna be here. I've been doing this a long time. You can trust me on it. This is my 11th year teaching stats. Seen this every year. You're gonna be okay. So until next time, have a great day.